Today we want to talk about the mole, and I do not mean that little furry animal that runs around, nor do I mean the blemish that might be on your skin, but I'm talking about the chemist's mole. And the definition of a mole is a basic quantity of matter. So I want to try to imagine what a mole really is and to show you what a mole is. First of all, a mole is a count. We're familiar with counting things. We know that we might, count pennies. Over here, I have some pennies. And I say, I could start counting all of these pennies, which would be quite a few. But let's count out 1, 2, 3, 4, 5, 6, 7, 8, 10, 11, 12. There's a dozen pennies. So dozen really is a number also. I could go ahead and count out 144 pennies, and I'd have gross of those. I could go and count 6.022 times 10 to the 23, and I'd have a mole of pennies. So basically the word mole is a count. Now, it'd be very difficult to count 6.022 times 10 to the 23, Avogadro's number. We just would be counting forever. Once my students, I figured out, what if we were to count to 1,000,000? It would take you 11 days to count to 1,000,000 by counting right. So we have to have a better way of counting things. One idea would be to know how much a dozen pennies weigh. So I'm going to do this for us. And I'm careful to have all pre-1982 pennies because they weigh about 3 grams, whereas after 1982 they only weigh 2.5 grams. And I'll put these on the balance here. These dozen pennies weigh 37.07. Okay? So I would think, what if I put another dozen on there? 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. We hope that it's going to double 37, which would be 74. So I'm getting about 74 on the weight of this. So basically, if I don't want to count dozen, I could basically weigh the pennies and divide by what I would think I'd tell you how many dozen. I would divide by 37 my weight, and I would end up with how many dozen pennies that I have. It's an interesting idea, but it's a very useful one. We have basically many ways to get the amount of something. You might imagine yourself going to a grocery store. And if you go to a grocery store, you would were asked to buy milk, you would buy a certain volume, a quart of milk. Or if you're going to buy hamburger, you'd buy a weight of hamburger, so much a pound. If you were to buy oranges, you might buy a dozen. So in the grocery store, we do buy things of a certain quantity by volume, by mass, or by counting. It's obvious if we bought a dozen grapefruits, that's going to be a whole lot heavier to carry than if we bought a dozen tangerines. So the same number of things does not have the same weight or the same volume. I would like for you to take a look at these particular bottles. Here's some chemical substances. Here we have water, and in there is 18 grams of water, and 18 grams of water is 1 mole of water. The second substance is sodium carbonate, Na2CO3, sodium carbonate. The bottle is almost full volume-wise, and the actual weight on that is 106 grams. So 18 grams, that's a mole of water. 106 grams is a mole of sodium carbonate. And here we have table salt, sodium chloride, NaCl. And it's 58 grams equal 1 mole. So what we see is different amounts equal 1 mole. So let me make some interesting comments here for this. A mole equal the amount, AMT, of the substance. And so we're going to talk about by count. It's equal to 6.022 times 10 to the 23 particles. That might be an atom or a molecule, whatever. It's equal to the molar mass, or the formula weight, in grams. So let's go back to our three substances. We said that 18 grams of water is a mole. How would I know that? Well, basically I look up water, which has the formula of H2O. I go to the periodic chart and I observe that hydrogen has an atomic mass of about 1, and oxygen has atomic mass of about 16. So in order to get that straightened out, I see I have each atom, a mole of hydrogen atoms is about 1 gram. 2 moles, because I have the subscript 2, is about 2 grams, and oxygen is 16, so 2 plus 16 is 18 grams, equal 1 mole. And we could do exactly the same thing with sodium carbonate. Let's actually do that, because this brings together some of the things we learned before. We know that sodium, symbol is sodium, Na, and we know that it has a +1 charge because it's in group 1A of the periodic chart. You'll find it over here, sodium, in the first column. So it has a +1, and carbonate is a polyatomic anion, and you have to know those by heart. It has a -2. So because it's -2 and this is +1, we have to take 2 of those. So this is the formula for sodium carbonate. Now, to get a mole of sodium carbonate, we're going to have to know the molar mass, or the formula weight, in grams. And the way in which we'll do that is we'll look up sodium and we'll round it up. We're going to estimate this. It would be 23. So we're going to have 23, and we have to multiply it by 2 because we have 2 of them. We have carbon. And if we look that up, it's going to be 12. And then we have oxygen, 3 of them, 3 times 16. And we'll sum that up. We'll do this on the calculator so that we don't make a mistake. And besides, we know how to use our calculator. Okay. So basically, I'll go 2 times 23 equal plus 12. I tend to plus the quantity, 3 times 16, end of quantity, equal 106. So what does that tell you is that for sodium carbonate, so 106 grams of sodium carbonate equal 1 mole of sodium carbonate. And we could do the same thing with sodium chloride. We know the formula for sodium chloride is just NaCl. And we'll just do that. Sodium is 23, and chloride is 35.45, and that equals 58 58.45 and grams per mole. So the molar formula weight in grams, or the weight of a mole of sodium chloride, is 58. And I think I just said 58 or rounded it off to 58 grams. So it's very convenient in chemistry to be able to weigh out a mole or a part of a mole or a fraction of a mole. And we certainly cannot count atoms. So we're going to use this information, and with the knowledge that the moles, the formula weight of a substance in grams is going to equal 1 mole. Now, let's see types of problems that we had. I might ask you, how much is a half a mole of sodium chloride? So how many moles, and we do our problem this way, question mark, moles of sodium chloride. That's what we want. And what I'm given is I ask you how much a half a mole is. So I'm going to say that this is what I want, 0.5 mole of sodium chloride. And then I have to multiply by a conversion factor made out of an equality. And we already have this equality, 1 mole of sodium chloride equal to 58.45 grams of sodium chloride. So that is our equality. From the equality, we're able to make our conversion factor. We'll choose this to be in the denominator, 1 mole of sodium chloride, so that the moles of sodium chloride cancel, and this to be in the numerator, 58.45 grams of. And so all that remains is to multiply that, 0.5 times that, and that answer will be equal to 29.7. I've taken half of it, but I'll just do it by the calculator to make sure. 58.45 times 0.5 is equal to 29.225. So basically 29.225, probably could grams. So to weigh out 29.23 grams would be 1 mole, 1/2 of a mole of sodium chloride. A more interesting and maybe a more difficult one would be to ask you how much 100 atoms of iron. That's what I have, 100 atoms of iron. What would that weigh? Well, basically, the mapping would be like this. You're going to have to go from atoms to moles to grams. And that is solving this problem requires the use of 2 conversion factors. So let's say then, answering the question, how many grams of iron? I'm going to use the symbol for iron, which we know to be Fe. That's what I want. That's what I want to know. And what I'm given is that I have 100 atoms. Now, we have to use 2 conversions units. What would be the conversion between count, atoms? What would be the conversion unit between count and atoms and moles? And we've said it before that 1 mole of iron is equal to 6.022 times 10 to the 23 atoms of iron. Okay? And then the second I'll have to go, so I have the mole there, a relationship between that and the atom there, and then I have to also go that 1 mole of iron equal its formula weight or atomic weight in grams. And if I look that up, I'll see over here, here's iron, 55.8 grams. 55.8 grams of Fe. So finally, all that's left to me to answer this question, and I'm going to answer this question up above here so they can see all this information. So I start out, grams of Fe equal 100 atoms of Fe times my first conversion factor, which is going to take moles, it's going to take atoms to moles. So I put the 6.022 times 10 to the 23 atoms of iron. Put it there so it'll cancel per 1 mole of Fe. Okay? Now, one more conversion unit. I'm now into moles of iron. Come down and use this one. That factor, 1 mole of iron is 55.8 grams. So 55.8 grams of iron per 1 mole. And you notice when this agrees with what I want, I have my problem set up. And so now all that remains is to do this calculation. And I wanted to do this calculation for me because I want to make sure that you remember how to enter a number like 6.022 times 23 in your calculator. So I'll clear that. So that problem says take 100, 100, and divide it. So I'm divided by 6.022 times 10 to the 23. So I'm going to be 6.022, enter the exponent, EE, and it's positive, so it's 23. Okay, equal. Every time I divide, you want to say equal. And then I'm going to multiply, without even looking, times 55.8. And that is equal to, I'll take that up here. I'm going to make sure you see that decimal point in there. Equal 9.266024 times 10 to the minus 21. I'm putting in brackets because I'm just writing what I see off my calculator. However, as you know, that would not be your correct answer because I should not have any more than, at the most, if there's a period here at the end, I have 3 significant figures, so I'd have to say 9.27 times 10 to the minus 21 grams of Fe. And that's the answer. So in this chapter, you need to get in the manner of thinking about moles. You know, my friend Beaker is a chemist. And Beaker doesn't think about dozens or gross or anything. Everything he thinks about is in moles because he's a really good chemist. And so if you really want to think like a chemist, you have to ask, how many moles of this do I have? And you got to get to it by either weighing. You can't count atoms, but you have to know Avogadro's number, 6.022 times 10 to the 23. That's the number of particles in a mole. And another interesting thing is that if I have a mole of water, H2O, that means I have 6.022 times 10 to the 23 molecules of H2O. But if I wanted to count the atoms, I would have 6.022 times 10 to the 23 atoms of oxygen. But because it's H2, there are 2 atoms of hydrogen in every molecule. I'd have double 6.022 times 10 to the 23 atoms of hydrogen. So this is this is chapter 6. The main idea of all of chapter 6 is what is a mole and what is the particular aspect of it. So read that chapter and study and do the problems assignment, and hopefully you got a better feeling of an idea of how to use the mole in chemistry.